Today we are walking through the paper titled Recursive Multi-Agent Systems. The paper asks whether collaboration between language model agents can be scaled by recursion, in the same spirit that a recursive language model deepens reasoning by repeatedly refining a latent state.
So the focus is not just making one model think longer, it is making the collaboration loop itself deeper?
Exactly. The proposed framework is Recursive MAS. It links heterogeneous agents into a loop, lets each agent generate latent thoughts, transfers those thoughts to the next agent, and repeats the system-level collaboration over recursion rounds.
What limitation in previous multi-agent systems motivates that design?
Standard text-based multi-agent systems pass messages by decoding hidden states into tokens, then making another agent read those tokens again. That makes collaboration expensive. The paper's key move is to keep communication inside the latent space. Instead of turning every intermediate thought into words, Recursive MAS uses a small learned module called Recursive Link.
On this architecture diagram, what should I talk first?
Start at the left. Agent A1 receives the input context and produces last layer latent embeddings. The inner link refines those embeddings inside the same agent. Then the outer link maps the produced latent thoughts into the embedding space expected by the next agent. After the last agent produces latent thoughts, so the full multi-agent system becomes a loop computation, not a chain of one-off text messages.
You said there are inner and outer links.
The inner link works inside one agent. It takes that agent's last layer embedding and produces a refined latent thought that stays aligned with the same agent's input embedding space. The outer link works between agents. It includes an extra linear mapping so a thought produced by one agent can become a usable input embedding for a different agent, even when their hidden dimensions or embedding spaces differ. The residual connection matters because the link changes the embedding while preserving the original latent semantics. That is how the paper tries to make latent transfer lightweight, instead of rebuilding the message as text.
Can you connect that design to the equation for the inner link?
The inner link equation defines the transformed latent thought. It takes an embedding H, sends it through the linear layers with a GELU non-monetary, and adds the result back to H as a residual update. The reason this equation appears is practical. The method needs a small trainable bridge that can generate in distribution latent thoughts without forcing the model to decode and run at every intermediate step.
How do they train the whole loop instead of just training each link separately?
Training has two stages. First, each agent is warmed up in parallel, so its inner link can produce latent thoughts that match the semantic distribution of that agent's input embeddings. Second, the outer loop trains the entire multi-agent path across recursion rounds. The forward arrows carry latent outputs through the agents, while the backward arrows assign credit to the recursive collaboration path.
What is the advantage of staying in latent space during that recursive training?
The paper compares the cost of two ways to pass intermediate thoughts. Text-based recursive collaboration has to project each latent embedding into the full vocabulary space. Recursive MAS instead transforms each latent embedding with recursive link. Their analysis says the text root includes an extra term proportional to latent thought length times vocabulary size times hidden dimension. The latent root replaces that with a term proportional to latent thought length times hidden dimension squared.
That explains speed. What about the claim that recursion actually improves answers?
The first results view shows scaling behavior. In the sequential light setting, increasing training and inference recursion rounds generally raises accuracy across math, science, and code benchmarks. For example, the top row reaches its strongest cells at deeper recursion. MATH 500 rises to 78.4, IIME 25 to 35.3, GPQAD to 33.6, and code generation to 38.3. The point is not one isolated benchmark, but the repeated pattern as recursion deepens.
Does the method only work for a single sequential chain of agents?
The lower half tests that recursive MAS is instantiated across mixture style, deliberation style, and distillation style collaboration patterns. It beats the compared standalone or role-specific agents in the shown benchmark groups, rather than depending on one fixed system shape. A concrete example is the mixture style MetaQA group, where recursive MAS is at 61.7 while the specialist agents shown are at 48.1, 43.3, and 29.0. On AIME 2026 in the same group, it reaches 46.7 compared with specialist scores of 10.0, 13.3.
How does the paper summarize the overall empirical comparison?
Across 9 benchmarks spanning mathematics, science, medicine, search, and code generation, the paper reports an average accuracy improvement of 8.3% over advanced single-agent, multi-agent, and recursive computation baselines. The same comparison reports 1.2 times to 2.4 times end-to-end run speedup, plus 34.6% to 75.6% token usage reduction compared with text-based recursive multi-attempt collaboration.
Can we see the speed claim on a result figure?
Yes, this speed chart compares recursive MAS with recursive text MAS across recursion rounds. In the first round, the average speedup is 1.2 times. In the second, it is 1.9 times. The pattern matches the complexity argument. When recursion deepens, avoiding repeated text decoding matters more, so the gap over recursive text MAS becomes larger.
And what about token usage?
The token chart shows the same direction. Relative to recursive text MAS, recursive MAS uses fewer tokens by an average of 34.6% in round 1, 65.5% in round 2, and 75.6% in round 3. That is the main trade-off the paper wants us to notice. Recursive MAS adds learned latent links, but it removes repeated text communication, which is exactly where recursive multi-agent systems can spend a lot of time and tokens.
What are the limitations or open risks I should keep in mind?
The evidence is strong for the evaluated settings, but it still depends on training recursive link modules, selecting a latent thought length, and testing within the chosen collaboration patterns and benchmarks. The ablation notes that performance improves as latent thought length grows, then tends to saturate around a moderate budget near 80.
So the conclusion is that recursion becomes a system-level scaling tool, not only a single model trick.
That is the paper's central claim. By keeping collaboration in latent space, recursive MAS makes recursive multi-agent reasoning more accurate, faster, and less token-heavy than text-based recursive collaboration in the reported experiments. That wraps up this paper walkthrough.